Okay, so today is back to reinforcement learning day. It's been a while. I've been pretty focused on TensorFlow Quantum and QML applications, but I've been meaning to get through Sutton and Barto, so I need to get through it. And it's just continuing from the last time, which is talking about 2.5 through, let me see if 2.7 is today. It's going to be short. So first things first that we are discussing is the non-stationary problem. So previously, we talked about just the stationary, where you're learning, these the bandit problem, where if you pull a lever, that probability distribution is stationary, i.e. the mean and standard deviation doesn't change. However, you can have non-stationary problems, and the key here is it's pretty straightforward. So if you remember the Q update rule, oopsies, Q, there's no states in this. Then we just take it and do 1 over the app and 1 over the number of times the action was taken times the reward minus. We can just change this value to be between 0 and 1. And this will tell us how much we should weight the future reward. So, as this number gets very large, normally as n increases, this value decreases. But you'll often see this. This is basically in like DQN or even in actor-critic methods. This is basically the gamma parameter, which is almost always set between 0.95 and 0.99 in modern reinforcement learning settings. But that's just an interesting note. And so that's pretty much all there is to non-stationary problems. You just can adjust that value. And then we can get into a technique to improve the performance or the learning of the bandit algorithm, which is optimistic initial values. Optimistic. So this allows, if normally we set the Q values all equal to 0, but we can set them actually equal to whatever we want. So if we just start them off with a higher value than is reasonable, then we can sort of avoid the epsilon greedy problem of, if we always want to take the best action, but how can we explore if we always take the best action? We're never going to explore. But if we set everything to, a high level, these are the arms, this is the reward, they're only going to decrease. If this is above even the maximum reward level, they're only going to decrease down to the norm. So this is always going to be, at least for the initial part, this is always going to be an overestimation, which means we're not going to have the same levels of difficulty exploring, because we're going to want to take this action. If normally we start off with 0, and let's just say the true values are here, here, and here. We're going to look at each of these, and if we act without epsilon greedy, we're always just gonna, it's possible that we could just, if we observe this value, we observe this value, and we observe this value just due to chance, we might always take this action when it's not actually the best action. Whereas with optimistic, we can see that if these are the true values, getting down to this point takes a long time, right? We're going to have to bump this down, 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 down. And so statistically speaking, it's unlikely to reach all the way down to this underestimation from an overestimation. And so it's easier to work with that challenge. So now we can see This done pretty simply in code. Let me zoom on over to it and zoom in. So pretty much the same code as last time. The only difference is we're just initializing the Q value to be 5s instead of 0s. That's the only difference. And so here we can see the figure. I also learned today when I opened a figure that you can actually open pictures in VS Code. I never knew that actually. And so we can go and see, this is a plot of the steps versus the average reward. This is slightly different than what figure 2.3 in the book is showing, because that's showing percentage of optimal polls. This is just showing numerical reward. We can see they converge similarly, but there is this advantage at the beginning. Next, I will X out of each of these. And next we have a very common and very important algorithm known as upper confidence bound, UCB. And so actually in the book, they might do it later. I haven't read the whole thing, but in that little section, 2.7, there's not really any explanation for what it is. So I'm going to start off with something different than how the book does it. Give a little more explanation of, where the hell this thing came from. And so specifically, if you've ever taken a machine learning class, you'll know about the Hofstede bound, or I think that's how you say his name, Hofstede bound. And so we're going to derive from that the upper confidence bound. And so if you're not familiar, here's a little clip about the importance. You should know about the statistics behind this because it's very important. So here I'll show this is actually my machine learning professor on the importance of the bound.
Pin down this picture mathematically, and the answer is yes. Okay, and it is a gift from Hofstede. And now I'm going to just state the gift from Hofstede, and I'm going to go through it slowly because it is a complicated formula, but it is a very, 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 very important formula. Okay.
So you can see the very important formula in terms of the statistical importance, has a lot of far-reaching implications. Basically, the bound says the inequality says the probability that you have this these independent variables. You have this probability that x minus the expected value of x is greater than or equal to epsilon is less than or equal to e to the 2 negative 2 n epsilon squared. And so where here n is oopsies, I miswrote that. Oh no, I didn't miswrite it. It was just a variable confusion. Where epsilon is basically our confidence. Let's see. And n is just a number of samples. So what is this telling us from, if we're looking from a statistical perspective? So the difference between our average drawing of x, that is average. So basically, how far off is our guess? If we want the expected value, which we always do, how far off, or maybe I should say incorrectness, how far off is our guess of the expected value, basically? And so at most we wouldn't want this to be a huge number. We want this to be as small as possible, basically, because we want this accuracy to be high. And so this is basically saying that as we increase the number of samples, because you see this right hand side is only dependent on the number of samples, not anything else. As we increase the number of samples, this goes down, which means that this probability, the probability that we this error is greater than E, goes down as well, which means that as we sample more, we get a better estimate. Now that's not really surprising. That seems, stunningly obvious, but it's important classification and formalization of exactly how we do this. So now we can see, you're probably thinking, okay, what does this have to do with Q-learning? What does this have to do with the bandit algorithm? Well, let's just rewrite this. If I do, if our if we say that this is our estimate of Q of A, right, is the average, and so Q star is always the true Q value. Is really what this is. And so this is basically like what we're trying to approximate, right? And epsilon is less than to equal to e to negative 2s. Here steps is number of iterations, epsilon squared. So now, what do we want? We want this bound right here. We want to know how good our Q value is so we can, add to it and augment it to choose the best action. So now we need to just essentially solve this equation. But you'll notice that we want this to be as small as possible. We want the chance that we are wrong, the probability that we are wrong, basically, or wrong to a certain degree, to be low. And so we say we have this right-hand side, and we want this to be, some small number, which we can call P. Is not good because it's probability. I'll just call it P, whatever. And so, you could set this to just some small number, whatever that might be, or you could, what is commonly done, well, let's solve for it, right? So we want epsilon. That's our goal. So what do we do? First thing we do is we take the natural log. So we do negative 2 epsilon squared equals natural log of P. Then we divide by negative 2. So negative 2s. So we have epsilon squared equals negative natural log of P over 2s. I should really rename this n of a, actually, now that I think about it. Let's say s equals n of a. Now we take the square root, and we have our answer. So we can say that, rearranging this formula, if we want our optimal, we can see that Q of A is greater than or equal to Q. I should do this on a new page. We can see that we have Q of A, Q star. So the optimal value is greater than or equal to, if we're explicitly solving for it, we can do minus Q of A So now we do Q star A greater than or equal to, we have Q of A plus epsilon. Notice you're probably wondering how I maintain the, this should be a minus sign. You're probably wondering how I kept that the same, and that's simply because epsilon just depends on the square value over here, and I could set this epsilon just to be negative. And so continuing on, so therefore we know that, hence this is why it is called the, I really can't draw this thing. This is why it's called the upper confidence bound, because it takes this Q value to the, and gives it a bound such that it brings it up to at least this equal to, and so, or a maximum of equal to this, such that this is always going to be, well, probabilistically greater than this value. And so we already saw that we can therefore choose an action. We already saw what the epsilon is. So we do the max of A, the max action of Q of A plus negative natural log of P over 2 N of A. Now, you won't see this very often. You'll almost always see UCB, upper confidence bound 1, which says P equal to T to the negative fourth. And so if we do that, we can simply solve. We can see that negative natural log of T to negative fourth equals 4 natural log of T. Cancels out with the 2. So we'll see the epsilon UCB1 equals the square root of natural 2 natural log of T over N of A. And that's the one you'll almost always see, but that's just saying P equal to, and so that's basically, the P is basically how confident we are. And so as T increases, we're getting, our understanding should be that we're getting more and more confident. We want to choose the one that we're moving towards being optimal. And so this sort of automatically, this is sort of like epsilon decay almost, in the fact that, early on, this is going to be a very small value or very large value, which means we won't really have a lot of confidence in that estimate, because remember, this p-value comes from what we're setting this equal to. And so this is our, confidence in our estimate. Basically, we're saying, okay, our confidence in the estimate is this p. And so, if the p is very high, that means we're not very confident, because it's less than or equal to this value. And so if that value is very high, then it's not a strong bound. And so we can see this is pretty easy to show in code. If I just go over, do it, and there we go. We can see that we have UCB one and the normal one. We can see it's just straightforward. We take the Q values, an array of them. We do the square root of, in this case, negative log of P, or in this case, 2 times log of T. Notice that this here is just to prevent division by 0 errors, because n is initialized to 0. And so we just add a very small value, which means that this will be this will be extremely large, right? 1 over 1 to the negative 8th. It's a huge value that will always get picked. And so then we can simply show a comparison of the p. Here I set p equal to 0.1. Here p equals t to the negative 4th. And here we have just normal epsilon equals 0.1. And this is pretty much just the standard. This is exactly as done before. I'm not going to go over the details of the code because the only difference is just the action selection. And so we can see, I zoom in a little, we can see that UCB, both of them, go to achieve a better bound or achieve a better reward than this epsilon. And that's because, you might think, okay, it makes sense that they achieve it faster, but why is the policy they achieve better? And that's because there's always some randomness in this epsilon policy, whereas this upper confidence bound sort of learns, quote unquote, to take it out, because as this t increases, our confidence increases as well. So we can choose, once t is 1,000, we have 1,000 to the negative 4th. That's a small number. 1 over 1,000 to the 4th is a tiny, tiny number. And so we have that term effectively goes to nothing almost. And so we have that confidence term. So we basically just choose greedily once we've done enough exploration. And so that's why it's a really powerful tool. And this is just, and you might be wondering, you'll notice right down here, it skyrockets up, very much so. And that's actually, I believe, yeah, that's exercise 2.8. Why does it spike at the 11th step? And so that's because it chooses every single action, because the 0 number taken means it's incredibly high. It always chooses every action at least once. And so you see down here, it's stuck choosing every action. It's forced to choose those actions, but then it skyrockets because it's like, okay, now I'm choosing now I can actually choose the best action, not just ones I have to explore. Unfortunately, the unfortunate thing with this whole setup is that, unlike here, where let's suppose you have a function approximator or a neural network, which you often do nowadays, for this Q value, right? You can choose greedily super easily. It's trivial to do. However, if you have this upper confidence bound, the number of times taken each action, this changes once we have states to consider. This equation, epsilon greedy doesn't care about anything. It completely independent of your environment, of your algorithm, of anything you do. However, this one, this is dependent. So if we have, this looks easy to do when we have no states, but if we have state dependent things, so then we have, notice upper confidence bound for, it's basically never gonna exploit because there's so many state action combinations. That's why we're using the function approximator in the first place, is that the state space and the number of actions are just so huge, we can't use dynamic programming or something. And so we can see this is common with bandit algorithms, but not harder to apply to contemporary deep reinforcement learning techniques. So that was 2.5 through 2.7. Once again, all the code is available, and this book is also free. I have a hard copy, but you can get it for free online, legally too, I might add. The professors who wrote it made it available. So next time will be, I think, yeah, we'll finish off the chapter probably. We'll do the gradient-based bandit algorithm, and just finish up some summary. So yeah, that is all.